We're ready to move on from the first 5 reactions of glycolysis to the second half. And before we do so, I just want to take a moment and go back and make sure you see the big picture here. Our first 5 reactions were about an energy investment, and we know that we're now in -2 debt of ATP, having lost 2 ATPs. We've also split a 6-carbon molecule into 2 3-carbon molecules. Now, let's take that latter for just a second and make sure you see that. Here we took fructose 1,6-bisphosphate and we split it into 1 molecule of glyceraldehyde 3-phosphate and 1 molecule of dihydroxyacetone phosphate. But here's the really interesting part. In the 5th reaction, we made dihydroxyacetone phosphate into another molecule of glyceraldehyde 3-phosphate. So see, we now have 2 different GAP molecules, and from here on out, they're both going to go through the same thing. What that means is everything we do from now on is going to be done twice. We have to count everything twice. The second thing I want to review with you before we go on is where the ATP energy investment happened. I want you to pause for a moment and look at the first 5 reactions. 1, 2, 3, 4, and 5. I want you to figure out where did we invest the ATP. Pause, put that in, and then we'll come back and go over that. Okay, what we've done here is put an ATP in to the first reaction. And you can see that. The phosphate was transferred from the ATP to the 6th position of glucose. We'll put it down like this and show that the ATP is now gone and transformed into an ADP. We did the same thing in the 3rd reaction. An ATP becomes an ADP and the phosphate is transferred to the 6-carbon molecule, and those are both kinases. At this point, we're going to move on and talk about the second half, the energy dividend. We've invested ATP. We now need to recover our investment and actually make a profit. We're also going to talk about 1 oxidation reduction step. In fact, that's the first reaction, or at least the first reaction of the second half, reaction number 6. Let's move on to that and talk about it. That's going to be the only thing we talk about in this video because it's the most complex and interesting reaction in all of glycolysis. Okay, we're going to continue on our pattern, and the first thing we need to note is that reaction 6 is catalyzed by an enzyme we call glyceraldehyde 3-phosphate dehydrogenase. We sometimes call this GAP, DH. And DH is a critical type of enzyme that we want to discuss. We are dehydrogenating glyceraldehyde 3-phosphate, and you may remember that that means we're doing an oxidation reaction. One thing I always tell students is that when you do an oxidation, you must also do a reduction. What does oxidation mean? Well, remember, oxidation is losing a pair of electrons, or really a hydride ion, and reduction is gaining a pair of electrons, or a hydride ion. So if you're going to lose electrons, they have to go somewhere. Let's focus on that part of this reaction first. Let's go over here, and we have glyceraldehyde 3-phosphate. Remember, that's the product of the last reaction, reaction number 6. And we're going to transform that by oxidizing it. And what we're going to do is oxidize this aldehyde right there. Now I want you to just pause for a second again, and I want to ask you from our previous unit, when you oxidize an aldehyde, what do you get? Can you remember that? That's an important skill for us to say, what is 1 step of oxidation higher than an aldehyde? Well, keep that in mind as we move forward. Now, I told you that as you oxidize, you remove a hydride ion, which is a proton and 2 electrons, and they have to be put somewhere. What we're going to do is we're going to take that hydride ion, this pair of electrons, and we're going to dump it in this basket to make NADH. Now remember, I like to call NAD plus a basket, and I like to call NADH a basket with a hydride ion in it. Its purpose is to hold on to a hydride ion that we strip from our food. That's why I like to call this NAD ... H, because it's really about the electrons. The proton just comes for a ride. Now, do you remember what happens when you oxidize an aldehyde? I hope that you would say you get a carboxylic acid. Let's go ahead and put that down for a second here. In some ways, that is what you get. However, that's only if you remove that hydride ion and replace it with a water. And here's the weird thing about this. This is what makes this reaction complex. We're going to take another substrate, an inorganic phosphate. You have plenty of inorganic phosphate floating around in your cells. There's no shortage of it. And instead of bringing a water in to attach to that particular carbon, we're going to bring in a phosphate. So that oxygen, O-, is going to attack the carbonyl, and it pushes that pair of electrons away. And instead of getting a carboxylic acid, we replace that hydride ion with a phosphate. Now, one thing I always tell students when we're messing around with reaction arrows is that an arrow becomes a bond. Where's the new bond that we just formed? It's right there because this oxygen attacked that carbon. Now, here's what we have. We no longer have glyceraldehyde phosphate. We have a glycerate molecule because that's really a buried carboxylate right there. And we're going to call this molecule 1,3-bis phosphoglycerate, or just for short, 1,3-BPG. This is a really important molecule. Make sure you understand this. We went from glyceraldehyde to glycerate. That's because the carbon that was the aldehyde is now a carboxylate. Here's another question for you. Pause and tell me, what type of linkage do we have between this phosphate and this molecule over here? What's the linkage? We practiced this in our previous chapter. See if you can do it. Okay, here's the answer. This linkage is an acyl phosphate, or an AP. How much is that worth? If we were to break that linkage, how much energy could we get? Well, you may remember that's worth 50 kilojoules per mole. Now, let me put it this way. Over here, we have a phosphate. That's just nothing. It has no energy to it at all. And all of a sudden, we attach it onto this carbon, and we have a 50 kilojoule per mole currency. It's like dropping a penny and looking down and seeing a $50 bill. It's almost like magic, but it's not. Let me tell you what exactly is going on here. The oxidation reduction of the aldehyde drives the formation of an AP, an acyl phosphate. Again, that's an incredibly valuable molecule. An acyl phosphate is something we can spend. It's a currency. Maybe you can guess what we're going to spend it on. That'll be in the next reaction. Let's sew this one up first. Let's say we haven't gained any ATP and we haven't lost any ATP, so our accounting is still at -2. That's this important reaction. It's a tough one because it's got 3 substrates, NAD+, PI, and GAP, 2 products, NADH and 1,3-bis phosphoglycerate. Let's go on and show you what we're going to spend that powerful acyl phosphate on in the next reaction.